Freefall. Introduction. The purpose of this lab is to create a change in energy time graph for an object in freefall, where the system is the object falling and the Earth, and the surroundings are anything that could act upon the object other than gravity, although this is nothing in the case of this experiment. Models and fundamental physical principles. A computational model simulating the object in freefall and energy changes of the object Earth system being studied was used. Additionally, the fundamental physics principles of the energy principle, gravitational force, kinetic energy, and potential energy were all also used. Preview of results. The change in position of the object in real life seems to be around the same as what the simulation predicts. Additionally, the change in energy graph created looks as what the change in energy time graph of an object in freefall should look like. Main physics ideas used. The main physics ideas used were the force of gravity and potential energy, kinetic energy, the energy principle, and the position and velocity update formula along with Newton's second law. How all these were used and why they were used will be discussed as we discuss the coding and as we discuss in the discussion. Here's a screenshot of the object in Tracker. The object was actually in projectile motion, but I took the position of the object from the apex of its trajectory to right before it hit the ground, and I only focused on the y direction, and due to this, it could be the data is the same as what it would be if this object was in free fall from this distance, and that distance being the apex of its trajectory. Code. The object's mass was set to the appropriate mass, and its position was set to the appropriate position. Technically, the position vector had a value in the x direction, but since we're assuming it's an object in free fall, the motion in the x direction can be omitted, so the position vector in the x direction can be set to 0. Additionally, since at the beginning of the observed frames, the object is at the apex of its trajectory, it is at rest, so the velocity vector is 0 for all values. Here at the top, you can see how the kinetic energy was put in terms of the ball's velocity and mass, along with the gravitational potential energy and then the total energy of the graph. Then, as you can see here, is in the middle is the iterations, where the force of gravity on the ball is calculated, and Newton's second law is used to derive the velocity and position update formula, and these are used to calculate how the object's position and velocity change over time. And here at the bottom is once again the total energy, kinetic energy, and potential energy due to gravity formulas and how they changed over time used to construct the change in energy versus time graph. Here is a picture of the output of the code. As you can see, like I said, since we're only worrying about motion in the y direction, it is essentially an object in free fall, and due to this, the object in the code simulation is just in free fall. Here's a photo of the change in the y position as time continues and the change in energy as time continues. As you can see, the change in the y position is very similar in real life as to what it was in the model, except for here at the end, and we will discuss why we think potentially it is like that in the discussion. And the change in energy versus time graph is exactly what we would expect it to look like, and we will also discuss that more in the discussion as well. Discussion. Now, in this, if you look at the energy versus time graph, the total change in energy was always 0, and this assumes that no work is done on the system, and this assumes that there is no force done on the system. And you would assume an object in freefall has a drag force acting upon it. But this exact object in freefall was studied in Physics Lab 2, and these were the findings of Physics Lab 2. The observed position and predicted position without drag were very close throughout the 0.267 observed seconds. The observed position was seen falling faster than the predicted position without drag. Since drag would push up on the paper ball against the force of gravity, it should make the ball slow down and fall slower than the predicted position without drag. Since this is not the case and how similar the observed and predicted position without drag are, drag can be assumed to be negligible in this experiment. Due to the findings in Physics Lab 2, there was little to no drag working on this object, so drag can be assumed to be 0. And I cited Physics Lab 2 in the end of this, so if you want to go check that out, you can. Similarities and differences. The change in position of the object in real life in the y direction seems to be around the same as in the simulation, except for a noticeable discrepancy at the end of the observed motion of the object in real life. And I think this discrepancy might be that in the final frame of the observed time, the object might have hit the table for a second, causing it to not go in the motion that it should be as if it was still in free fall. Additionally, the change in energy graph created looks as what the change in energy time graph of an object in freefall should look like, with the change in kinetic energy increasing as time goes on, and the magnitude of the change in potential energy increasing as time goes on, and the change of total energy being 0 because there's no work done on the system, and the change in kinetic energy and change in potential energy cancel each other out. Possible sources of error. In this code, if you make the delta t value too big, it was inaccurate. So I had to make it as small as possible, and if you made delta t too small, the code actually crashed. So a potential source of error could be that the delta t is too large. Another source of error could be that the center of mass is not perfectly plotted in Tracker. And as mentioned, another source of error might be that the object hit the table in the last observed frame. What does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. In the computational model, the energy principle is satisfied as delta k plus delta u gravity all cancel out to give a value of 0 for delta e, which is expected as no work is done on the system, aside from drag, but drag was found to be 0. What if? What if drag was not 0? If drag was not 0, then delta E would not equal 0, as drag would do work on the object as it is falling, and delta E equals work done on the system by the surroundings plus Q. This would make delta E not equal 0 and would also change the delta K and delta U values. Here is my references and the link to Lab 2. Thank you.